Welcome to Pomodoro Joe for Saturday, March 11th, 2023. Today we're doing LeetCode problem 109. Convert sorted list to binary search tree. This is a medium problem. Given the head of a singly linked list where elements are sorted in ascending order, convert it to a height-balanced binary search tree. And height-balanced, oh, look at that, that's cool. A height-balanced tree is a binary tree in which the depth of the two subtrees of every node never differs by more than 1. So this is basically just saying the depth is balanced. All right, so it helps to look at our example here. We have a singly linked list and it's converted to a binary search tree. Things to note, it is already sorted in ascending order. So, as demonstrated by our example here, that means that the center node, the middle node of our linked list, will be the root of our binary tree. So this is going to be a recursive algorithm. Generally, when I deal with trees, recursive algorithms are my go-to algorithm. In this case, looks like we need to find the middle node. That becomes the root of our tree. Then we split our list and look at just the left side of the list, and that becomes the left side of our tree. And we split and look at the right side of the list, and that becomes the right side of our tree. So we recurse. We'll grab the center node, we'll recurse on the left side of the list, and we'll recurse on the right side of the list, and assign those to the left and right branches of our tree. And voila, we are done. All right, let's see, we have some constraints. Between 0 and 2 times 10 to the 4th number of nodes. Okay, pretty straightforward. So we will put 25 minutes on the Pomodoro timer and we will get started. All right, so with any recursive algorithm, the thing you need first are your base cases. So the base cases are the cases in which you are done with your work and you can return. No recursive calls. So what are the base cases here? Well, the first one that comes to mind is if this head node is empty. So if we don't have a node, we'll just return none. That's our first base case. All right, what about if the head node has no next node, if we're at the tail? Well, in that case, we can also just return, well, no, we'll return a tree node with just the value of the head node. All right, so if our head is the tail, we basically only have a 1 node list. We'll just return a tree node with that value. Otherwise, now we'll have to find the midpoint. Now, finding the midpoint of a linked list can be a little bit tricky. There are a couple ways we can do this. One simple way to do this is just create a list or an array out of our linked list, and then we can have an index into our nodes. But there's a way we can do this just using pointers in our linked list. So I'll show you how to do that here. Okay, so very similar to finding cycles in a linked list, we can have a slow pointer and a fast pointer. The slow pointer will just increment, will go to the next node in the list every time through our loop, and the fast pointer will go through 2 nodes every time through the loop. That means that our fast pointer is moving twice as fast as the slow pointer. So when the fast pointer gets to the end, it's moved twice as far as the slow pointer, which means that when the fast pointer is at the end, the slow pointer must be at the halfway point. So that will find our middle node. We can even start the fast a little bit ahead. So that'll help out a little bit. But we have to be a little bit careful here because our fast next could be none. So we'll only do this if the fast next is a node. Okay, so this will give us basically our midpoint. Our slow pointer here will be the middle node of our tree. Now there's one thing we do need to do. So if we are going to pass in the left and right lists to our recursive call, we actually need to make the left list have an endpoint. Otherwise, it will just keep going through the entire list. So we actually have to break our linked list at this point. We need to essentially find the node just before the middle node. We have to break its connection to the middle node, creating a new endpoint for our left list. So let's see, that means we're going to have to keep track of that previous node. Okay, so now as we go through our linked list here, we're going to keep our previous node. So the previous node will be set to the slow node, and then we advance the slow node, which means that the previous node will always be pointing to the slow node. Now that we've found the middle node, we can do our recursive calls. All right, so we'll need to create a tree node here with the value of our middle node, which at this point is slow. And then we need a left and a right. Well, this will be our recursive call. So let's see. We'll call this on the left list. Okay, the left list actually still starts with head. And the right list will start at slow next, because slow is the middle node. Now the right list already terminates normally with the end of the list. Now the left list, however, we need to change this a little bit. So before we call our left, we need to set our previous next to none. This is breaking our list, but we need to do this in order to have an endpoint for our left-sided list. But we can always fix that up here. So after we do our recursive calls, then we can just say prev next equals slow again. So we break the list temporarily for our recursive call, then we fix it back up here. This way we don't have any weird side effects from somebody calling our function. We're trying to be good citizens here. And at the very end, we do need to return our root node that we created. Okay, and that should be it. Let's see if this works. Okay, it seems to work. Let's see if we can pass all the tests. And we do. All right, and we do okay. We beat 63% for runtime and 26% for memory, so that's not too bad. There are a couple things we can do to speed this up. I guess I'll go through them. They're not super intuitive, and they probably won't make a huge difference in terms of our speed, but there are things that we can do. So one thing we're doing here is we're keeping this previous and this slow. We might not need to keep both of them. Let's just see if we can do a couple things here to maybe change this around. So our previous is equal to slow here. Slow gets slow next. Then we have the slow value. Previous next is none. But previous next is just our slow. Okay, so what can we do here? Well, if we early out here, let's see, I'm trying to think through this a little bit before I just jump into coding. Okay, so our previous is equal to slow, which means that if we, and then slow has advanced. So this slow is slow next. So that's the previous next. So we could change this. Instead of just saying slow value, this could be the previous next value, because the previous next is equal to slow. So we just changed slow to previous next here. We could also do that down here. But we've already messed our previous next up after this. So we have to do this before we break our list. And it doesn't look like it makes any difference where we do this. Oh, but we need to do this first. Oh, that's the root right. Never mind. Okay, we just need to do this previous next none before we call the left, because we have to break that connection. So it looks like by using previous next in place of slow, we actually don't need our slow anymore at all. I guess we need it here. But we could, let's see. We could do, let's see, how do we do this? We can call it the midpoint. How about that? There we go. Let's call this mid, and it's the previous dot next. And that means we can just do this. The midpoint value. And this can be the midpoint next. Previous next we will set to none, but then we'll set it back to the midpoint here. We cached it out, we're resetting it here, just to be good citizens. And that actually looks pretty good. We got our root, we got our right, and then we do our left. Let's see if this still works. We've kind of rearranged things a bit. Let's see if it still works. Still seems to work. Let's see if it saves us to anything. At this point, it probably won't. It actually makes things worse. 34% for runtime, 49% for memory. But this is all one step along the way, because our next step is, if you notice down here, we're not using slow at all anymore. At this point, we kind of don't need this slow. But if we got rid of this slow altogether, that's going to cause some problems, because we still are keeping track of where our middle node is, and we still need to basically have this cascade here. Unless we can exit early. Maybe if we exit early. So if we break out before we get to this point, now we don't need this check anymore because we're checking up top here. Okay, which means I think at this point, we don't need this previous anymore. This previous basically will be the slow because we're exiting one early. It's a little bit hard to describe. Now we don't have this anymore, but that should just be slow. We don't have this anymore. So it looks like if we do this, we might be, we might be unable to reconnect our list at the end. I guess that's the trade-off between speed and doing the right thing. I'm starting to second guess if I even want to go down this path. Yeah, I might not want to do this. All right, well, I think that's the best I got for today. We beat 63% for runtime, 26% for memory. Not great. There are definitely ways to sort of speed this up by jumping ahead. It's just a little bit too tricky. I don't want to get into it too much. And it might mean that you have to break your input list, which I also don't like doing. So that's it for me. Hope you enjoyed this. Hope you had fun. Hope you learned something. Hope you can try this one on your own. Again, this is LeetCode 109. And yeah, I hope you can get a better score than I did. 90% or better. Go for it. All right, hope you enjoyed this. Hope you had fun. Hope you learned something. Hope you can go out and write better code.